We all know the drill. We get older, our joints start to ache, our vision blurs, and eventually our bodies break down. It feels like an unavoidable law of biology, a painful reality we simply have to accept. But when you look at it strictly through the lens of evolution, getting old is actually a massive puzzle. Natural selection is famously obsessed with keeping us alive and reproducing. So why would it permit an organism's body to spontaneously fall apart? To solve this, we have to look at how evolution filters out genetic mistakes. If a mutation pops up that causes fatal harm early in an animal's life, that animal dies before it can have babies. Natural selection cleanly deletes that harmful trait from the gene pool. This animated timeline shows how this dynamic shifts. Right in the middle is the reproductive threshold, when an organism passes on its genes. Notice how early fatal mutations hit an invisible wall and get filtered out. But mutations triggering after that threshold coast right past the filter. Natural selection is completely blind to them. Over millions of generations, that late-acting genetic baggage starts to stack up. It silently accumulates, causing the physical structure to degrade. That slow pileup of hidden, unfiltered mutations is what we experience as aging. Human aging represents a massive, long-term evolutionary blind spot. It is the cumulative weight of genetic errors that natural selection never had the chance to filter out. You might assume every vertebrate on Earth deals with this blind spot in the exact same way. They don't. Take a look at these amphibian cells. Many amphibians, reptiles, and fish possess extraordinary maintenance tools. They can rapidly divide and rebuild damaged limbs and organs, and they often stay highly fertile right up until the end of their extremely long lives. Then there are the mammals. Whether a mammal's maximum lifespan is 3 years or 100, every single species in our branch of the family tree is locked into a pattern of rapid, obvious physical decline. We become frail, our cognition slips, and cancer rates spike. If the rest of the vertebrate family tree has access to these robust tissue-repairing maintenance tools, why are we mammals operating without them? To find out where our cellular repair kits went, we have to trace our family tree back to our first true ecological enemies, the dinosaurs. Biologists call this the Longevity Bottleneck Hypothesis. It's a scientific framework suggesting that the extreme ecology of deep time permanently constrained mammalian genetics. During the Mesozoic Era, early mammals were mostly tiny, nocturnal insectivores. They scurried through the undergrowth in the dark, trying to survive at the absolute bottom of a lethal food chain. For well over 100 million years, dying peacefully of old age simply was not a mathematical reality. Almost every early mammal lived fast and ended up as a reptile snack before they ever reached midlife. When your life expectancy is measured in months, investing biological energy into long-term tissue maintenance is a complete waste of resources. Any genetic pathways designed to keep a body healthy into old age became useless biological baggage. Evolution is incredibly pragmatic. If a species stops actively using a biological tool, random genetic mutations will eventually disrupt it. And since that tool isn't needed for survival, natural selection won't bother fixing it. Comparative genomics points to a specific disruption in our lineage. This diagram illustrates a DNA repair mechanism used by almost all life on Earth, from bacteria to birds, to fix cellular damage caused by the sun's ultraviolet radiation. Watch how this glowing patch swoops in to seamlessly fix the fractured rung. Mammals are entirely missing this specific tool. In the mammalian version of the model, the patch disappears and the damage builds up. Because our deep-time ancestors hid in the dark, they absorbed minimal UV radiation. Combined with the fact that they died young anyway, long-term DNA maintenance was entirely irrelevant. Over tens of millions of years trapped in this high mortality bottleneck, random mutations quietly dismantled these protective genes across our entire branch of the evolutionary tree. We didn't passively drift into bad aging. To survive the age of reptiles, the mammalian lineage actively threw away its deep-time anti-aging toolkit. Then, roughly 65 million years ago, a massive asteroid struck the Earth, wiping out the non-avian dinosaurs and erasing the apex predator threat overnight. This sudden ecological vacuum gave mammals their chance. Without giant reptiles hunting them, they stepped out of the shadows, diversified, and quickly evolved into much larger forms. The pantodonts are a great example.
They were the first group of mammals to get truly massive, reaching up to 42 kilograms as they thrived in a newly safe world. But the fossil record holds a depressing twist. When researchers analyze the bones and teeth of these large pantodonts, they find that despite their massive size and the total lack of predators, these animals still lived and died incredibly fast. The external physical environment changed in a geological instant, yet 100 million years of fast-aging genetic programming hardwired into their cells could not be easily rewritten. Fast forward to today. Some mammals, especially humans, have managed to stretch our lifespans far beyond the few short months our Mesozoic ancestors experienced. This chart reveals the fatal biological flaw in our modern longevity. As our lifespans shoot sharply upward over time, our baseline cellular repair capacity remains completely flat at the bottom. We are surviving well into old age, but we are doing it without the genetic repair tools that other long-lived vertebrates naturally possess. If we look inside that biological deficit, we find the source of our most common ailments. Cognitive decline, failing joints, and cancer show up right here. They are the inevitable results of outliving our own biological warranties. The physical deterioration we experience today persists as a genetic echo of our time at the bottom of the dinosaur food chain. You can take the mammal out of the Mesozoic, but you can't take the Mesozoic out of the mammal.